Welcome to the 1978 Nobel Prize in Physics, which is another divided prize. And normally with divided prizes, I can kind of find some commonality or at least some common applications in between the two. This time I don't see that. So if anybody watching sees the commonality between these two, please drop me a comment or send me a DM. I'm racking my brain. I can't find it. But the prize was for two things. The first half of it went to Pyotr Kapitsa, who's a Russian. I'm sure I'm pronouncing that name wrong, but his half was for his basic inventions in the field of sciences and lab equipment and his discoveries in the area of low temperature physics. Some really cool stuff. The other half of the prize was shared between Arno, Penzias, and Robert Wilson for their discovery of the cosmic microwave background radiation. And that's some pretty cool stuff too. And we'll talk about both of them in a minute. But one of the things that I'd love help with is what is the commonality between these two? I'm just not seeing it. Maybe there isn't any. And it would be the first time I could think of that a prize actually was for two completely different things that just happened to be in the same year. But these weren't even worked on in the same year. One of them was worked on decades before the other. So let's dive in and take a quick look and see what the applications of these are. And by the way, with the cosmic microwave background radiation, I got a little surprise for you on that one. So there's some recent work in that area that lead us to believe that we might have been a little bit off on this one. So let's take a dive and see what's going on. So Pyotr Kapitsa, his work in low temperature physics is an interesting work. It's a field that had a previous Nobel Prize way back in 1913 when that went to Kamerly Ons, who was the first person to produce liquid helium, which is some pretty interesting material. Now, the reason this stuff is important when things or materials or substances are cooled down to really low temperatures, their properties change dramatically. Same thing like when they're raised to really high temperatures, their properties change dramatically. Now, think about it for a second. If you don't understand the material properties of my coffee mug or a heat shield or something at very high temperatures and very low temperatures, when you're trying to build a space program, it's not going to go your way, right? Because it's very cold in space, it's very high on lift, very high temperature on liftoff. Re-entry is incredibly hot, so you've got to make sure you understand how everything's going to react at those different temperatures, or you're going to kill people in your space program. So all this stuff is really important. For more reasons than a space program and industrial purposes too. That's just the most dramatic case of it. So way back in 34, Kapitsa developed a method for producing liquid helium in large quantities, which had never been done. People were producing little tiny bits of it here and there, but he came up with a way to really do it in large quantities, which was very important. Then in 1937, he figured out that at very low temperatures, liquid helium flows without resistance and becomes a superfluid. And then he kind of got busy during World War II. He was involved in the Russians' version of a lot of development programs. The world of physics kind of stopped for him and a lot of people, and kind of all efforts were devoted to the war. He actually was involved in their nuclear program for a bit. In the 1950s, he invented some high-power microwave gear and he discovered some never before seen high-pressure plasmas, which is weird because plasmas are a very strange thing, and the environments he was looking at them in were not normal environments for a plasma. So he did some really cool stuff at weird pressures, weird temperatures, and in weird conditions. All of which was greatly contributing, including the superfluid stuff. Now, superfluidity is when a fluid can move without resistance, so it doesn't slow down; it just sort of goes and goes. It's like superconductivity in that regard. So it's cool stuff, and it is very important to different things in the field of physics. But for life of me, I can't figure out what it has to do with cosmic microwave background radiation. So let's dig into that, and maybe somebody can help me make the connection between those two. Now, cosmic microwave background radiation. The interesting thing about cosmic radiation is every moment of every single day, the surface of the Earth is hit with some amount of radiation from outer space. Sometimes it's a little, sometimes it's more. It just depends on what it is. Our magnetospheres block some of it, but depending on the wavelength range, you get more or less of it. Sometimes you get neutrons, you get all kinds of things from space. Now, initially, it seemed like it got weaker when the wavelengths got shorter, and you could kind of predict what it was going to be at any given wavelength range. But then along in 1964, these guys were working on some measurements of radio signals from space around 7 centimeters, which is in the microwave band. And what they found was that the signal was a lot higher than what they expected. And they kind of were like, well, that's weird. And they did the same thing I would have done. The first thing I did was, hey, look, my experiment doesn't fit the known theory. there must be something wrong with my experiment. I got to go check on my gear. So they checked their gear. They called people in. They adjusted everything. They calibrated everything. It was right. People measured it somewhere else and got the same thing. And what they found was this cosmic microwave background that exists. And what it does, it's really cool stuff. It kind of continues all the time. It's this weird hum at 7 centimeters. And depending on where you're looking at in space, it can be a little bit different. But it can give you a lot of information about different things. For instance, it is some of the prime evidence of the Big Bang. At least we suspect it's evidence of the Big Bang. Maybe we're right, maybe we're wrong. It's still a theory, and you can't really tell, but we'll see. But it does give some credence to that Big Bang theory. It does carry a lot of information about the early universe, and but one of the things that was really interesting to me was when I first learned about this stuff 20 years ago, well, further back than that, but when I first really studied it as a professional physicist, 20 plus years ago, it we were like, okay, well, that helped us determine the age of the universe. And then we said, great, that's the age of the universe. And that's what's been in textbooks kind of forever. And now James Webb is up in space, and James Webb is taking a bunch of measurements, and the data we're getting from that says, not really. Hold on a minute. It's actually about twice as old as we thought it was. So I actually when I was researching this particular video, I actually sent some emails to some physicists I know going, hey, does anybody have any, stuff that says we've actually gone back and relooked at that cosmic microwave background and said, let's rerun those numbers and see if we had that right in 64. And maybe we just measured wrong. Maybe there was something else off. But James Webb, why is there disagreement between these two? And let's understand what that disagreement looks like. And honestly, I will, when I find out, I will put a video on that on my channel because I think it's kind of cool that scientists keep questioning themselves and saying, are we right? And we get new instruments and we measure things again and we say, oops, we kind of got that one wrong. It should be self-correcting. That's the way things should work. When we make mistakes, we should come back and say, hey, look, we were incorrect. It's actually different based on this new evidence. But based on the evidence they had at the time, it worked. So there will be follow-up to this video, I promise you, because the disagreement between James Webb and cosmic microwave background measurements now has me kind of confused and concerned in ways. But I'll find out more about that. We'll get back to you in another video. But if anybody can figure out a connection between these two, please drop me a line. I'd love to hear about it because I just can't figure it out for the life of me. So I hope everybody's enjoyed this video. We'll talk more about the cosmic microwave background and those measurements on James Webb. Won't be in a Nobel Prize video. It'll be in the Science Matters playlist, but it will be there as soon as I hear back from some folks. So hope everybody's enjoyed this video. Please don't forget to click like and subscribe, and we'll see you on the next one.